So I made a substantial revision to the key, posted that last night. People generally did fine on the first one. A few people seem to want to say that the maximum discharge, so discharge, we're just talking about the volume flux per time of ice. So some people seem to think of that as stuff leaving the glacier. We're just talking how much mass is moving here, how much ice is moving, and that occurs at the equilibrium line altitude. You just add up the mass balance, it's positive in the accumulation zone, and then it starts getting negative in the ablation zone, and so you reach that maximum where the mass balance is 0 at the ELA. Okay, number 2, almost everybody got part of that wrong. Most people got like what the deal was with yield strength, what we're doing there. But then the fact that I'd given you an equation that set yield strength equal to shear stress said, oh, well, what determines yield strength must be the things that determine shear stress. No, those are two independent things. We simply set them equivalent for our own convenience at equilibrium. Okay, so shear strength, or that yield strength, is a material property of the ice. And what we're doing is saying, okay, at this equilibrium condition where we're neither thinning nor thickening the glacier, the shear stress at the base equals the yield strength of the glacier. And we solve that for whatever we want to solve it for. In the case of your labs this week, you can either solve that, if you have the moraines, right, and you know some depths and some ice thicknesses and ice slopes, then you can solve there for what the yield strength actually is for that glacier. Once you know that, you can say, okay, I've got my ice thickness here, let me solve for the slope, back that up and do that over and over to extrapolate and fill in your glacier, your ice surfaces. Yeah, Miguel.
So I brought you like an equation that I've had from the notes, but how do you know which equation to use? Because if you get yield strength equals this equation, but it also equals this equation, so you say it depends on these equations, but you didn't put the other equation. How do you know which one to use in which sense?
Well, you just have to know what the equations mean, then, don't you? So, I mean, I know that's a really wild thing.
I mean,
but
I wrote
you
the
do.
same equation, and then I wrote the change in height over change in x. Which
Yeah.
is the same equation you wrote on here above that. Or what I should have put, and then I got marked down.
Yeah, that's because, okay, what did I write down? I wrote down on the board last time, I wrote down, okay, we can set yield strength equal to the shear stress. And the shear stress equals the ice density times its thickness times gravity times the, what did we say, right? I can't remember whether I used a D or a delta in that, but so that's the shear stress. If I set the yield strength equal to the shear stress, that's the condition at equilibrium. This is something that we'll do when we talk about landslides. We're saying, okay, I've got a material property. I've got in this case, a shear stress due to gravity. Let's find out, well, when they're equal, that should be when the glacier thickness is at equilibrium, more or less. I mean, it's all a somewhat of an idealized approximation that we're making when we write that equation. But what it implies is simply that we are using the fact that at this certain condition, the shear stress is equal to the strength. That is, the material property determines what, well, essentially what we're using is we're saying, well, the material property is going to determine how the ice thickness and the and the ice slope act, or how, you know, what goes on with that. But that doesn't mean that when I say what determines the yield strength for a particular glacier, i.e. if it's not the same for all glaciers, what makes it different? Well, these changing ice depth or ice slope don't inherently change a material property of the ice. That material property of the ice is dependent on particularly the temperature. So colder glacier is going to be more viscous. A warmer glacier is going to be less viscous.
Can thickness lead to a warmer glacier though?
No, but it can lead to greater pressure and putting it closer to the pressure melting point.
Okay.
And yeah, make the ice, so it is, you know, I will grant you that it's a gray area. You know, it's like, okay, the ice thickness may actually affect could actually have some effect on the yield strength. Typically, we try not to think of it that way, just because it's convenient not to. It's much more convenient if we don't have to be adjusting this while we're solving for that. So we just consider this to be a constant, and then use that relationship at equilibrium to solve for one or the other of these. But yeah, I mean, again, I'll grant you that's sort of a, kind of, I guess. And Michaela, to get back to your question, well, this, you know, so I can write this condition. But what I need to know about that is that it's not always true, or it's not necessarily always true. It doesn't have to be true. What I know about that is that, in general, then, if my ice thickness, for example, gets too thick, then my deformation rate will speed up and the ice will thin, and I'll get back to, that'll help bring me back towards the equilibrium thickness. If the ice gets too steep, similarly. Or if the ice is so thin that everything slows way down, then it'll bunch up and thicken up and get us back towards this condition. So again, in order to employ this equation, we need to know what it, we just need to know what it says. That this is not saying that the material property of yield strength is dependent on these things. This yield strength is a function of, well, in particular, the ice viscosity. That's probably the main thing. And we know that the ice viscosity is kind of complicated. Glaciers are complicated. That's why we're making but they're complicated in a way that does allow us to make this sort of approximation. Remember, again, we're saying that we can take this strain rate law, right, where this is shear stress and this is strain rate, and if it looks something like that, we're saying, well, we can approximate roughly in here that that's going to be our yield strength. And again, this curve is essentially a material property of the ice, and therefore that, where the appropriate place to draw that line for the yield strength is also a material property of the ice. Yeah.
So just to clarify, that equation you can use to solve for yield strength, but those are not the factors that actually
right.
control
we at least to first approximation, this is independent of these.
Okay.
But essentially what we're saying is, well, these are dependent on this.
Okay.
This is our independent variable in this case. And then we might have others, right? And like you said, well, we can use these to figure out what yield strength is, but that doesn't mean that if I suddenly double the thickness of my glacier, I've now doubled the yield strength.
Okay.
I mean, it might affect it, but
So if
in
you
general,
were
no.
to do what yield strength is dependent on, would you say temperature and viscosity, or
Yeah, in general, temperature is the main thing that's going to affect the viscosity.
is there a better?
Or just sort of where the temperature relative to the pressure melting point is probably the more appropriate answer, right? Because you could be colder but still quite at the pressure melting point, and that would have the same effect as being warmer if the pressure were smaller, right? But ultimately, it is essentially a factor of this ice viscosity, which we know is a complicated sort of property. That, it's not. Viscosity is not a constant, but that is if we were, remember this, maybe this is getting too far into the weeds, but if we were talking about water and viscous flow of water, and this is a linear fluid, the slope of that line is the viscosity. The slope of this line varies all over the place. So the viscosity is a bit complicated, but still you can think of the viscosity as being, as the shear strength depending on that effective viscosity of the ice. Okay? Let's see. I was trying to think of like the perfect analogy for what's going on, like when a glacier slides. And I thought of one. I don't know. Maybe this helps. So I could have a lot of so I could have a lot of water pouring through the glacier, and it could actually be coming out the other end. But as long as there's enough restriction on the amount of water that can come out the bottom of the glacier, then the pressure will stay high. It's like a hovercraft, it's got that apron, right? And it's blowing air. It's not like the air isn't escaping out the bottom, but the apron is inhibiting it enough to essentially levitate the hovercraft. But if I suddenly obliterate the apron, then the hovercraft crashes because now I've opened up the gates and I can't maintain that pressure despite the, still having the same airflow. Now it's escaping too quickly. So I don't know, maybe that might help a few of you. Maybe I've just, at the risk of confusing most of you, maybe some of you will get something out of that. The other thing I thought of was, what's going on when it drains? Well, it's like, I keep thinking of okay, if I've got a straw filled with water, what's the right manipulation here? And essentially, we're just talking about, well, if I've got a straw and I'm holding the bottom of it and it's filled with water, what happens when when the sliding stops is that I've taken my finger off of the end of the straw and the water's drained out. So, yeah. Trying to think of, was it actually any more complicated than that? No, it's not actually any more complicated than that. I could be trickling water in at the top of the straw and trickling a little out at the bottom, but anyway, as long as the result of that is to maintain that height of the water, as soon as that water level drops, then I've lost my water pressure, and now my glacier is not going to float anymore. Because that's essentially what's happening with sliding. The glacier is not, if it were literally floating all on water, it would just fall off the hill, right? But, so it's not, but, it's kind of floating. It's sort of like a ship run aground in a sense, or a ship partially run aground. It's still kind of scraping along the bottom, like, when you go canoeing or kayaking or something in low water and have to drag across a gravel bar or something, at least there's some water in there to help you pull that canoe across. Okay. Any questions? Or should I talk about? Oh, yes.
I was just wondering about, so when I look at the keys on the quizzes, do you expect that much writing for Because
You keep asking me this, and I keep saying, no, of course
there's like
not.
an immense amount of writing in those that I just don't know how to
I mean,
put inside of
look, in those things, that's another opportunity for me to be verbose, Michaela. You know, in those. Okay, kidding aside, what I'm trying to do there is I'm trying to. Okay, why did they not understand this? Because, you know, so I'm trying to both explain the answer and give you the correct answer. You know, essentially give you the correct answer with enough words that you actually understand it, and then hopefully you can then communicate it back to me at a later date without just sort of reciting the words and actually understanding what you're right. That's the idea anyway. Any other questions? That's a good question. Because in case it's not clear to everybody, no, I don't expect you to write as much as I typically write in some of those answers. Now sometimes I will go back and say, okay, I could do this a lot shorter, more succinctly, but you know, at other times it's like, well, I need to add a little more explanation here as to what's going on. Sometimes I'll be really explicit about that. Other times I just sort of count on the fact that you are all intelligent people and sort of figured that out, especially now that I've told you a couple of times. We good? All right. I want to talk about hill slopes. We'll see how far we get with this today, because now we're 20 minutes in. But that's all right. I got this time and next time to talk about essentially why are hill slopes convex, or another way to think about it is sort of what I said about last time. Well, what does the convexity or the degree of convexity, like the sharpness, the curvature of a ridge top, say, tell us in general about a landscape or a lowering rate? And so, you know, again, the hilltops are convex, but you know what? The toes of not all the hill slopes don't always have. Okay, let me just sketch this real quick. You know, right? That's convex, the very top of my slope. But you know, what happens down here? Does it keep getting steeper? Does it do that? Sometimes we've actually got a concavity down here. So let's, you know, and that may tell us something about the why they're convex. But let's just look at least a couple of cases to see if we can figure out what's what. Oh, and it's already up there. It's just turn off the lights and pull the screen down. Yes, it's there. That's good.
It says light dimming.
What's that?
It says light dimming.
Yeah, I see that, but like, why? Let me just fire it up again. It might just be sort of a sleep mode. There we go. So this is one of the spots we'll go to on Saturday. Bring rulers, bring shoes that you can clamber around on this slope in. It's supposed to be a beautiful day, but you know, I always bring rain gear to fend off rain. You know, if you don't bring your rain gear in Oregon, it's just kind of guaranteeing. You're just like asking for trouble, right? Anyway, so here we have Chip Ross Park. Here's a photo. Here's the LiDAR. This is the bare earth hill shade LiDAR with color, green to red, according to the slope. And so we see this nice, big, broad, relatively low slope ridge, but getting quite steep, and steeper and steeper and steeper until we get all the way to that bottom of that little ravine there. So yeah, that's a thing. Now here's a relatively different sort of case. These are some moraines up on, this is Broken Top and this is Broken Hand over here. If you're familiar with that area at all. Three Sisters Wilderness, west of Bend. And this is kind of cool. The next slide I'll show you essentially looking end on to this part of that moraine right there, so you can see the, you know, it's relatively sharp up at the top. Pretty much kind of planar, near planar slopes on the sides, and if we look at the LiDAR and the slope coloring, we see that, yeah, that's what we saw. Essentially, we were looking in that last view, we were looking right up at this point here. So what do we got here? We've got some very sharp ridges and near planar slopes, although, you know, tapering off into flat areas adjacent to the moraines. Some places where we can see some evidence of past mass failure. You know, okay, sometimes this thing is just sort of maybe gradually smoothing it by frost heave, but maybe occasionally you get, you know, you can even see the headscarf there. You can get some mass failures that are inconvenient, so pay no attention to that. We'll talk about the other part right now. Okay, so in the first case, we've got a soil mantled slope. That's these soil mantled slopes bounded by these, maybe put it in quotes, streams. But I have seen water flowing down there. It just doesn't happen very often. So we've got some incision and lowering in those ravines, and then the whole slope is convex, and also soil mantled. We've also then, of course, in the second case, we've got piles of poorly sorted, unconsolidated sand, gravel, and boulders, and they're just sitting there slowly diffusing with some spots showing evidence of bigger collapses. So I started off with a kind of a statement or a question that I wanted to try to answer. That was, how do we get from soil flux is proportional to slope to the lowering rate is proportional to ridge curvature, which is something I've told you before, but just sort of tossed it out there like, yeah, we'll learn that this is true. So I might need to put some caveats on that. So I might start off by saying, well, the sharpness of the moraine ridges is probably not indicative of a landscape scale lowering rate, right? You know, what's going on at this moraine is not necessarily representative of really anything but what's going on at that moraine in terms of the lowering rate of these mountains. And I guess another caveat we might put on here is that with proximity to the Corvallis fault, I do wonder whether the incision of these ravines has been, I guess, fully transmitted to the ridge crests. And also, you know, I wonder a bit about the representativeness of this spot, where the diffusive transport process might not be representative. You know, basically here we've got gophers moving stuff around. A lot of the adjacent landscape, we're going to have transport probably dominated by tree throw. And so they might behave very differently, so the curvature of this ridge might not be indicative of the broader landscape for a couple of reasons. But, yes?
So that's a ridge? It looks like it's sitting in a depression.
You just need to like close your eyes and swing your head around a little bit. Because yeah, this is the high point. Yeah, if you can't see it, you know, it's like it can be really difficult to get it to flip. So let's just move back to this. We understand this, right? Down is down and up is up. Okay. All right. Now, it is worth, again, I wonder about whether the diffusive processes or the dominant diffusive process on those ridges there may not be representative of what's going on elsewhere with tree throw. Here's an example in the Coast Range, ridge, valley, and here you can see these very, pretty sharp ridges. This is supposed to be I think that's the same scale as that. So 100 feet is the scale bar there, and that's also a 100-foot scale bar. So the ridges are much sharper, but the slopes don't seem to get continuously steep or even reach the same kind of steepness that we saw at Chip Ross. But they're also really messy. We see these sort of planar-looking slopes, but kind of dimply. And that dimpliness is people have inferred, scientists have inferred that dimpliness is due to tree throw. That what we're seeing is when a tree gets thrown over, it creates a pit and a mound, and so we're seeing lots of pits, and we're seeing the result of moving stuff around huge chunks at a time. Whereas at Chip Ross Park, where the gophers are moving little bits at a time that don't really show up on the LiDAR. But here, the bits that are moving around do show up on the LiDAR. And incidentally, this is, you might also notice how different this spot looks than right over here. And that's because, this is like the cleanest, slipperiest clear cut that I could find for this sort of topography. Once you get under canopy, your point density for your bare earth LiDAR goes way down, and you just can't see as much under canopy. Okay. All right. So, it's time to do a mass balance or two. Today, maybe one, maybe another the next time. Let's start with that moraine type case. And this will also be similar to your labs next week, where you've got a pile of stuff, unconsolidated, in the case of the moraines, sand, gravel, boulders. In the case of your labs next week, you'll have sand and boxes. In the case of the moraines, probably frost heave, maybe a bit of rain splash. In the case of your labs next week, splash from sprinkler drops. Okay, but let's before I belabor that point too much, let's zoom in on a bit near the ridge crest. So let me first just draw a slightly not so zoomed in view. And this is all just unconsolidated stuff. There may be bedrock down here somewhere, but we don't need to worry about it for our purposes. And we could start looking at little boxes on here. And so let's just sort of pick one where we do see some difference in the slope on the uphill side and the slope on the downhill side, and draw a close-up of this spot. So, if that looks a little bit convex upwards to you, then that's on purpose. But it's a bit subtle. Let's just draw one boundary here, another boundary here. Again, this is all just stuff. It has a bulk density we'll call rho sub B. We can put a datum down here and use Z for elevation. we can mark down here our distance axis, x. And let's just say we'll call the uphill side x sub 1, we'll call the downhill side x sub 2 for what happens as we go forward. Okay, so I've drawn this box to encompass the surface and extend to some kind of indefinite depth. Because technically, I need to consider, okay, what are my various mass fluxes on all of these boundaries? So, for example, I can draw, a boundary down here and say, potentially I've got a mass flux. Maybe, well, probably not. I mean, now that's really going to be 0 unless there's sort of a lava dome starting up under here. Similarly, at the top, here I'm going to put an approximately equal 0, because I could have some, for example, aeolian, that is wind carried sediment coming in and out. But it's unlikely to, if this, moraines are kind of like big piles of boulders. It seems unlikely that a little dust coming in or out is going to have much of an effect. So let's ignore that, at least for the time being, and really forever. But not to say forever, but for this, forever in terms of this class. And so then on this boundary, we can have mass flux. And we're likely on this side, well, we might have a bit of noise. Some stuff might be coming out as well as going in, but likely quite a bit more going in than coming out. So, or actually scratch that, reverse it. And on this side, again, we've got another mass flux. And again, likely due to frost heave, but could be some other things as well. I'm just thinking in terms of moraine sitting up on a mountain at elevation, frost heave might be important. But again, here we're going to have an imbalance since we've got this relatively steep slope. But in this case, more going out than coming in. All right. So let's set up our mass balance. And we'll say, okay, I want to solve for my change in mass. And my change in mass is going to be, in this case, well, simply adding up the fluxes on either side and multiplying by time. So my change in mass is going to be my mass flux at x1 minus my mass flux at x2, and then multiplying by whatever time I'm looking at, whatever increment of time I want in order to figure my change in mass. And that's just very simple mass balance. Now, why have I chosen this is positive and this is negative? Well, stuff that we're using the convention that stuff moving in the positive x direction is positive. And so stuff moving in is positive and will contribute to our mass. On the other end, if there were stuff moving in the negative direction, that would contribute to our to our mass in there. But if we have a positive mass balance at the x2 point, then that's going to subtract from our mass. Okay. All right.
So mass flux is always a positive number, even if you're losing mass?
No, not necessarily. It could, I mean, mass flux would be, again, mass flux is positive if it's going to the right, it's negative if it's going to the left.
Oh, so,
Yeah, so we can have a positive change in mass, a negative change in mass. The only thing we can't have is negative time. At least not so far as I know. Okay, what's the mass? The mass, well, it's how much there is in that pile of stuff, right? But it's, so it's going to be the height of stuff in here times the width, and I'll draw in a, you know, a dy. Or let me make it a delta y at this point. I might have some distance into the board if I'm really wanting to say, well, okay, mass is volume times my density, and the volume and let's just be super strict about this. So it's going to be the average elevation, which is going to be z at x1 plus z at x2 divided by 2 times the lengthwise distance, which is x2 minus x1, times the increment into the board. So that's my volume. Let me make that 2 a little more like 2. You can see why I always cross my z's, because my 2's get pretty nasty sometimes. Yes.
So are you, for the first part of the equation, are you multiplying z times x1, 2, or is that?
No, this is that z elevation is a function of distance.
Okay.
This is, you know, while this looks two-dimensional, we're solving it as a one-dimensional problem. So z is elevation, and it is a function of x, so z at x1, z at x2. So yeah, good question. I want to be clear on that. Just for convenience, I'll go ahead and call this mess over here just the average elevation with an overbar. With an overbar, just indicating that's the average elevation in the box. And yeah, I'll just leave it at that for now. All right. So that means preserve our drawing here. So that means my mass over on my left side then, for my mass balance, I want the change in mass. So that's change. I'll just put a big delta for that. Change in z bar times x2 minus. Let me just put a times sign there so it's relatively clear what I'm. Okay, so change in elevation times the distance increment times the lateral increment times bulk density, and that's going to be equal to the flux at the side minus the flux at that side times, all right, so here I'm using flux, big mass flux Q as a function of x, so Q at x1 minus Q at x2 times delta y and delta t, which is what I'm going to call my time increment there. All right. Well, this is a little clunky looking for my tastes, maybe yours as well. Let's do a little massaging of this. First of all, let's see. We've got some constant terms here. This increment x2 minus x1 isn't changing. We're setting that to be our control volume. Our delta y isn't changing. Our density isn't changing. So we can take those out of the delta, divide both sides by them. Similarly, divide both sides by delta t. So that gives me delta z bar over delta t equal to, the other thing I'm going to do is reverse the order of these q's. So I'm going to have to have a negative sign. I've got my division by density. And q at x2 minus q at x1 divided by x2 minus x1. Okay, so it's still looking a bit clunky. This here we'll call delta x. This business here we can call delta q. So just change in flux. So that I can write my mass balance as, and I'm about out of time, so I'm not going to bother erasing all of that, but delta z over delta t equal to minus 1 over the density times the delta q over delta x. Now, can we just go ahead and everybody cool with me getting rid of these clunky deltas and turning these into derivatives? So if I do that, that is in the limit that delta x goes to 0, and in the limit that delta t goes to 0, my delta q delta x becomes a dq dx. This becomes a dz dt. I'm going to get rid of the overbar because now I don't have to worry so much about the average elevation. And, all right, check this out. The math guy in me, like the guy who's taken in several years of math in college, has to make these funny looking d's. Anybody seen these before? So let me just finish writing this up. Let's see a few nods. So anytime I've got an equation with derivatives in more than one variable, and I need to use curly d's, it's just an indicator that I'm only looking at the change in q with respect to x. I'm only looking at the change in z with respect to t. There's no other variable implied in there. It's not implied that I'm thinking of some total derivative. It's a partial derivative. So curly d means a partial derivative of that. I'm just about out of time. Yeah, I am. So I will pick it up there next time, because what we're going to then do is say, well, last time we figured out how to write down q in terms of slope and a diffusivity. And so once we plug that in, then we will quickly end up with what's known as the diffusion equation. but not for heat, as we've talked about it before, but rather for topography. All right, see you all next time.